In this segment, we're going to talk about the ideal gas law, when we can make that assumption, and how we can use what's called the generalized compressibility chart to help us make that justification for making the assumption that we've got an ideal gas. Now, we can evaluate thermodynamic properties of pure substances in the gas region or the superheated region two ways. Number one, if we've got thermodynamic tables, we can use those. Or if we've got an equation of state, a valid equation of state, we can use that. So an equation of state is just a mathematical relationship relating those thermodynamic properties that we might be interested in, such as pressure, temperature, and specific volume. And the one that you're probably most familiar with at this point is the ideal gas law. So the ideal gas law should look familiar to you. It's MRT equals PV. You can also divide through by mass to get specific volume. And what I'm going to focus on now is that R. So that R is the specific gas constant. It's specific to whatever substance that you've got. And it's a function of the universal gas constant, which is this pink R bar value that you see here, and the molar mass. So let's look at the molar mass. The molar mass is in terms of kilograms per kilomole or pound mass per pound mole. And those values can be found for various substances in table A1 and A1E. R bar, that's your universal gas constant, and it's just a constant, it's just a number. And these numbers are at the very bottom of your conversion factor sheet, so you'll have that on a test, you'll have that accessible to you. Those first two values, the 8.314 kilojoules per kilomole K and the 1.986 BTU per pound mole degree Rankine, those are probably going to be the ones that you use the most, but there's another one on there as well if you need that. So with that being said, now you've got another form of the ideal gas law that you can use. So you've got your specific gas constant, which is equal to R bar over your molar mass times the temperature, and that equals P times the specific volume. So you've got three different forms. Now your book, unfortunately, I don't believe they have the specific gas constants tabulated anywhere, so you'll have to calculate it based off of the universal gas constant and the molar mass. So just keep that in mind. So the ideal gas law is super simple to use and it's super convenient, but the question is, when can you use it? Can you use it anytime you've got a gas, or are there specific conditions that have to be the case in order for you to make that assumption? What we're looking at here is we've got a TV diagram, and this is for water. So you see the vapor dome, and you've got these lines of constant pressure that are horizontal in the two-phase region, and they go up in the superheated region. What we're going to ask ourselves now is, can we treat water as an ideal gas if it's in the superheated region? Now, in addition to those lines of constant pressure, you've got these little dots, and next to those little dots, you've got numbers, 0.0, 0.1, 0.8, and so on and so forth. Those values are the percent error involved in making the assumption or making the approximation that water behaves as an ideal gas at that particular state. So anywhere in the pink region, you've got a pretty low percent error in making the approximation that water behaves as an ideal gas. But in the white region, of course, that error goes up. Now, we're only talking about using or possibly using the ideal gas law if you're in the superheated region. If you're underneath the dome, then you've got liquid water. This is no longer something that you want to be looking at, so just be aware of that. It's only in the gas region. Now, what we'll notice is that at high temperatures, and when we say high temperatures, we mean relative to the critical temperature. At high temperatures relative to the critical temperature, we tend to be in that ideal gas range. And this is a relationship, or this is a trend that's valid for other gases as well, not just for steam. So, and then at low pressures, and when we say low, we mean low relative to the critical pressure, we tend to be in that ideal gas region if we're in the superheated region. Now, remember that critical temperature and critical pressure, that's the temperature and pressure at the very apex of that vapor dome, if you don't remember. So, for example, the line of constant pressure that passes through the apex of that dome, that's a line of constant pressure that would correspond to 22 megapascals. So that's the critical temperature. And the critical temperature is, I don't remember off the top of my head, but it's going to be between, I think it's 377 degrees Celsius, somewhere around that region. Now we can quantify how much a gas deviates from ideal gas law behavior if we use what's called the compressibility factor. So Z, that's your compressibility factor. It would be 1 if you've got an ideal gas, if you were in that pink region, right? And if it were less than 1, then you wouldn't have an ideal gas. Your substance deviates from ideal gas behavior by some amount, okay? And you can tell by how much it deviates by what your value for Z is. The further it gets away from 1, the further you're deviating from ideal gas law behavior. So what we're going to look at now is what's called the generalized compressibility chart, and that generalized compressibility chart tells us what the Z value is given a temperature and pressure of our gas. And the temperature and pressure of your gas, because the location, you know, the diagram that you see here, it's just for water, and so it's got a specific temperature and pressure, a specific temperature, critical temperature and critical pressure at the very apex of that dome. Well, for different gases, the location, that critical temperature and critical pressure are different. And so normalizing our temperature and pressure to the critical temperature and pressure is going to help us sort of to normalize the location of that vapor dome, if that makes sense. All right, so just in case it didn't, let's go on. So we've got our generalized compressibility chart here, and on the left-hand side, you've got your compressibility factor. That's your Z value, and the closer you get to 1, the closer you are to ideal gas law behavior. And then you've got some other stuff on here as well. On the x-axis, you've got your reduced pressure, your PR, and we'll talk about that in just a second. And then those little kind of wavy pink lines, that's lines of constant reduced temperature. And that reduced temperature is the temperature of your gas that's normalized to the critical temperature of your gas. So what you see here, that little blue ball, it's traveling along those lines of constant reduced temperature. So 1.3, 1.5, and 2. Anywhere along that topmost line, your reduced temperature would be 2. And then, of course, on the x-axis, that's where we put your reduced pressure, and that's the pressure that's normalized to the critical pressure of your specific gas. And those critical temperatures and pressures, you can look those up in Table A1 and Table A1E. Now what we're going to do is we're going to zoom in on just a small part of that generalized compressibility chart. So here's our zoomed in segment of that generalized compressibility chart, and we're going to develop some rules now. We're going to say that we can assume in this class that we have an ideal gas if our reduced temperature is greater than 2. So remember, if you kind of look back at, if you look at the full-blown version of this generalized compressibility chart, you can sort of see where those lines of constant reduced temperature are. So if you've got a reduced temperature that's greater than 2, then you can see you'd be way up at the top in that green line, that little green shaded area right there. So your reduced temperature is greater than 2. You could see anywhere in that green shaded area, it doesn't really matter where you are, you would have a Z value, your Y coordinate, be pretty darn close to 1. So we're going to say that if your reduced temperature is greater than 2, you can assume that you've got an ideal gas. If your reduced temperature is less than 0.1, you can see pretty much anywhere you are at, along any one of those lines, as long as your reduced temperature or reduced pressure is less than 0.1, you're pretty close to a Z value of 1. And now we're going to say as well, if your Z value is greater than 0.9, we'll go ahead and call an ideal gas assumption a good assumption to make. So that would put you near a Z value of about 1. Now you also see these other little lines that are going from the bottom left to the top right, or sort of off to the side to the right. Those are values associated with the pseudo-reduced specific volume, and your book talks about that a little bit. I'm not going to worry about that. I want to keep things really, really simple, and we're not going to use it in this class. But if you're interested in it, like I said, it's discussed in your book. So let's work a problem. Can we treat air as an ideal gas at 25 degrees Celsius and 1 bar? So, well, let's see. We've got some rules here. We say if our reduced temperature is greater than 2, or reduced pressure is less than 0.1, or our Z value is greater than 0.9, we can go ahead and assume that we've got an ideal gas. So that's or, right? If just one of those conditions is met, then we're good to go. So let's check the first one. Check our reduced temperature. So the first thing we need to do is look up our critical temperature. And remember those critical temperature values, those are in table A1, and it looks like for air, critical temperature for air is 133. So if I plug things into my equation here, and you need to remember, put that temperature, that 25 degrees Celsius, put that in Kelvin. Needs to be in absolute temperature units. See, we've got a 2.24, so first condition is met. Perfect. We've got an ideal gas. It's a good assumption to make. All right. Now we want to know, can we treat water as an ideal gas at 400 degrees Celsius and 33 bar? Well, let's see. There's our rules down there at the bottom, our 3 conditions. If just one of those is met, we can make the assumption that we've got an ideal gas. So let's check that reduced temperature. So the critical temperature for water is 647.3 Kelvin. So if I plug things in, and I got to remember, make sure I put my 400 degrees Celsius in terms of Kelvin. If I plug it in, I've got a reduced temperature of 1.04. So that's not enough for me to say I can assume I've got an ideal gas. So let's go on. Let's check our reduced pressure, see if that's good enough. Our reduced pressure is the pressure divided by the critical pressure, and it looks like in A1 my critical pressure is 220.9 bar. So if I plug that in, and my units need to cancel out, those reduced temperatures and reduced pressures, those are unitless parameters. Looks like I've got a reduced pressure of 0.15, so that's, according to my rules, that's not really enough. But not all hope is left. I've still got one condition I can check. I just got to check my Z value, which means I have to pull out my generalized compressibility chart. That'll be accessible to you on a test. Got to pull that out and check my Z value. So I'm going to look at the line of constant temperature that corresponds to about 1.04. That's pretty close to 1, so I'm somewhere maybe just a little bit above it. And then my reduced pressure is 0.15, so that'd be, actually it's a little bit that line should be moved over just a tiny bit. But you can see that where those two lines cross over one another, that's the location. And you can see that the Z value would be a little bit above 0.95. So that is enough for me to say, yep, I'm going to make the ideal gas assumption. All right, so let's work a problem. We want to know what the specific volume of air is at 25 degrees Celsius and 1 bar. So here's my given, find, assume solution. Okay, number 1, if you've got air, your first thought should be, do I have an ideal gas? Can I treat it as an ideal gas? If the problem statement doesn't say already that you can assume that you've got an ideal gas, most of the time you're going to be able to make that assumption. But on a test, I probably, if I don't tell you specifically that you do have an ideal gas, I want you to verify that assumption. So let's see if we can use our ideal gas law. Let's check my my reduced temperature. Check and see if that's greater than 2. Remember, I've got three things I can check to see if I can make that assumption of an ideal gas. So my temperature is 25 degrees Celsius, and you go ahead and put that in Kelvin. And my critical temperature from table A1 is 133 Kelvin. So if I plug that in, I see I get a reduced temperature of 2.24. So I'm good to go. And now I just need to apply the ideal gas law. So I've got my specific volume is equal to RT over P. That's my ideal gas law with Z equals to 1. And I need to make sure that I calculate what my specific gas constant for air is. And this is R bar over my molar mass. So my R bar, that's my 8.314. And then my molar mass, I can look that up in table A1 as well. And that's 28.97 kilograms per kilomole. So if I plug that in and I make sure that all my units are going to work out correctly, then I end up getting 0.86 meters cubed per kilogram. And we do work with air quite a lot. If you do the math, you'll see that the specific gas constant for air turns out to be 0.287 kilojoules per kilogram K. So if you couldn't remember that on a test, that's fine. You can use that. But if you don't, you need to remember to calculate it. So, all right. Well, I hope that was helpful, and thank you for watching.